Hello, my name is Kirk Weiler, and this is Common Core Algebra 2 by eMath Instruction. Today we're going to be doing Unit number 11, Lesson number 5, more work with sine and cosine. So in the last lesson, we learned how sine and cosine were extended to all types of angles, positive, negative, acute, obtuse, right angles, by using the unit circle to define these two important trig functions. Today, we're just going to work a little bit more with it. There's really not going to be too much that's new, but we want to try to get a little bit more comfortable with these amazingly strange functions. You see, pretty much every function you've ever worked with so far has been what I would call an arithmetic function, or a function that you could basically evaluate by using the rules of arithmetic, an algebraic function, if you will. This is truly the first situation where you've seen geometric functions, functions where the inputs are angles and the outputs are dictated by where you are on a circle. So let's begin by just reviewing the definition of sine and cosine. All right, recall the following definitions of sine and cosine. If theta is an angle drawn in standard position, whose terminal ray passes through the point xy on the unit circle, then the sine of theta is what, and the cosine of theta is what? Try to fill in what's at the end of those equal signs. Pause for a minute. All right, well, this was the entire focus of the last lesson and its homework, so hopefully you know that the sine is the y-coordinate and the cosine is the x-coordinate. So on that unit circle, it's now very, very easy. If I want to know what the sine of 90 degrees is, here I am. The sine's the y-coordinate. It's going to be equal to 1. If I want to know what the cosine of, let's say, 135 degrees is, I go over to 135 degrees. Cosine's the x-coordinate, so that would be negative square root of 2 divided by 2. All right. Now, I want to emphasize something else. Just keep in mind that just because these angles are listed on the unit circle doesn't mean they're the only ones that are important. We can clearly find the sine of 72 degrees and the cosine of 72 degrees, but that's where we have to use our graphing calculators. So make sure to have those handy. We'll need them for a little bit today. But I'm going to erase this, write down anything you need to. All right, and let's do a little bit of work. Okay, now I'm going to keep reproducing that unit circle diagram. If you have a larger one at your disposal, go ahead and be looking at it. But exercise 2 says, given the function f of x equals 6 times the sine of x, which of following is the value of f of 60? Well, this is simply function notation, right? F of 60 will be 6 times the sine of 60, all right? What's the sine of 60? Well, that's going to be the y-coordinate when we're at 60 degrees. Well, what is the y-coordinate when we're at 60 degrees? Here's 60 degrees, and the y-coordinate is root 3 divided by 2. The only thing else we might do is just cancel those and get 3 times the square root of 3. All right, easy peasy, right? Especially if we have that unit circle diagram sitting in front of us. And we know the definition of sine and cosine. Obviously, if you don't know the definition of sine and cosine, you're in trouble. All right, pause the video now and write down anything you need to. All right, I'm going to clear out the text. Let's do it again. If g of alpha equals 4 cosine of alpha minus 2 times sine of alpha, then g of 330 degrees equals, sorry for that. G of 330 degrees equals what? Well, again, this is simply function notation. Everywhere there's an alpha, I'm going to put in 330 degrees. So I have 4 times the cosine of 330 minus 2 times the sine of 330. All right, well, what is the cosine of 330? Well, it's the x-coordinate when we're at 330 degrees, which is root 3 divided by 2, minus 2 times the sine of 330 Well, the sine of 330 is the y-coordinate, and that ends up being negative 1/2. Now we just have to be careful. 4 divided by 2 gives me 2. So I get 2 root 3, and then I've got a negative times a negative, which is a positive, and of course 2 times 1/2 is 1. So there it is. All right, not too bad. Again, pause the video, write down anything you need to. Okay, I'm going to clear out the text. All right, see if you can answer number 4. All right, number 4 asks, which of the following is not equal to 1? Well, the cosine of 0 degrees, that'll be the x-coordinate at 0 degrees, and at 0 degrees, the x-coordinate is most certainly equal to 1. Let's take a look at number 3, the sine of 90. I don't know why I went with number 3 instead of number 2. Well, that's going to be the y-coordinate at 90, and the y-coordinate at 90 is most certainly equal to 1. So that's equal to 1. How about the cosine of 360? Well, I don't see 360 in my diagram. Oh, that's right, but a 360-degree rotation is coterminal with a 0-degree rotation, and that's also equal to 1. So I'm hoping choice 4 is the correct one. It says the sine of 270, well, that's the y-coordinate, and when I go to 270 in terms of my rotation, the y-coordinate's equal to negative 1. And I was looking for one that's not equal to 1. Negative 1's not equal to 1. That almost looks like an I. I don't want it to look like an I, given that we saw I earlier this year. So there it is. All right. So think about this a little bit, pause the video, and then we'll move on. All right, let's clear out that text. Okay. Exercise number 5. For an angle alpha whose terminal ray lies in the 3rd quadrant, always very important, any kind of information they give you about a quadrant, very critical. It's known that the cosine of alpha is negative 0.96. Which of the following is the value of sine alpha? Okay, remember, all of this comes from the unit circle. X squared plus y squared equals 1, the unit circle. And from this, in the last lesson, we had something called the Pythagorean identity, which told me that the cosine of an angle squared plus the sine of it, the same angle squared, would be equal to 1. Now in this case, we know that the cosine of the angle is negative 0.96. And what we're looking for is the sine of the angle. All right, so we set up this equation. Now we have to use our calculator to figure out what that is, but that's easy enough. That's 0.9216. It's not like I have it memorized or anything. Plus sine alpha squared equals 1. So I could subtract a 0.9216 from both sides. And I would find that the sine of alpha squared is equal to 0.0784. So now I'll take the square root of both sides, have to use my calculator, and I'll get plus or minus 0.28. Now, that's got to leave me, though, with choice 1, right? That's the only one that's even close. But why is it negative, right? Why is it that we can get rid of the positive version and it's only negative? Only negative. Think about that for a minute. Well, it's because we're in the 3rd quadrant. And in the 3rd quadrant, right down here, 1, 2, 3, the sine is going to be negative because the y-coordinate is negative. And therefore, our answer is choice 1. All right, pause the video now, write down anything you need to. Okay, let's clear out that text and go to the back side of the sheet. Now, what we're going to explore in the next couple exercises is the relationship between an angle, its sine and cosine, and the sine and the cosine of its reference angle. So let me remind you about something. Okay, if we have an angle drawn in standard position, don't worry about unit circle, that doesn't matter. If we have an angle drawn in standard position, let's say I had a 100-degree angle, okay? Its reference angle would be the angle between the terminal ray and the closest x-axis. So its reference angle, in this case, would be 80 degrees, okay? Reference angles are always positive, and they're always between 0 and 90, or in radians, they're between 0 and pi over 2, okay? And there's something curious about their sine and cosine and the cosine and sine of the original angle. All right, so let's explore that a little bit. Now for this, we're going to want our graphing calculators out. And it says, using your calculator in degree mode, determine the sine and cosine of both the angle and its reference. Round all answers to the nearest hundredth. All right, I'm not going to bring out the TI-84 Plus for this. I don't think that you should need me to do that. Why don't you go ahead and bring it out and figure out the sine and the cosine of all of those angles. There's 6 angles in total between A, B, and C. Go ahead and do that and round to the nearest hundredth where necessary. All right, pause the video now. All right, well, let's take a look. If we type sine of 110 degrees into our calculator, we'll get 0.94. Now let me pause for a second. If you didn't get 0.94 there, in all likelihood, it means that you were in radian mode and not degree mode. So what I would suggest doing, and I'll give you a chance to pause again, is if you didn't get 0.94, go into your mode and make sure you're in degrees. Let's pause just for a moment. All right. Well, let's get back to it. The cosine of 110 degrees, again, to the nearest hundredth, is negative 0.34. All right, so nothing particularly special about those values. But then, when we look at the sine of 70 degrees, 70 being its reference angle, we also get 0.94. And when we look at the cosine of 70 degrees, we get 0.34. So notice, these are the same, and these are almost the same, they just have opposite signs. And that kind of pattern plays out in every one of these. So for instance, the sine of 235 degrees ends up being negative 0.82. The cosine of 235 degrees ends up being negative 0.57. But then when we look at the sine and the cosine of its reference angle, 55 degrees, we get 0.82, and the cosine of 55 degrees is 0.57. So you're probably already starting to get the idea here, right? The idea that an angle and its reference angle have almost the same sine and cosine, the only difference being kind of that negative positive business. And it also plays out in this last angle. The sine of 282 degrees, 282, that should be a 2, whatever. The sine of 282 degrees is negative 0.98, very close to negative 1. The cosine of 282 degrees is 0.21. Likewise, the sine of 78 degrees, its reference angle, is 0.98. And the cosine of its reference angle, 78 degrees, is 0.21. Again, notice, same thing, but possibly with a different sign. Now, this happens for a very, very good reason, and I want to show you geometrically why it happens with just a single angle. All right, let's say I had my, my axes, and what will amount to being a pretty poorly drawn circle. But whatever, we'll get it. All right, and let's say I just draw an angle in standard position in the second quadrant, right? We know that the sine and the cosine are the xy coordinate, but we also know that this angle will be the reference angle. Now, if we took that point and we reflected it over, this would also be the reference angle. And what would happen is that these two right triangles would be congruent, right? The right triangle that's, let's do it here. This right triangle, they may not look congruent because of how bad my picture is, and this right triangle would be congruent. And therefore their heights, at least here, would be the same. Their y-coordinates would be the same, so the sines would be the same. And the x-coordinates would have the same length, just one of them would be negative and one would be positive. So reference angles are absolutely critical when it comes to the study of trigonometry. Because if we know everything about a reference angle, then we can do things with angles that have that as their reference angle. I'm not sure how much sense that made. Pause the video now, take a look at this, and then we'll work with the idea in the next problem. Okay, I'm going to clear it out. Let's take a look at the next problem. Make sure we're on my pen. All right. Given that the cosine of 30 degrees equals root 3 over 2, and the sine of 30 degrees equals 1/2, and you can get those from that unit circle diagram, determine the following values in exact form. Now, what in the world does this have to do with 30 degrees? Well, if I draw out a 150 degree angle, it's going to be in this quadrant, in the second quadrant, a 150 degree angle. Its reference angle, which for some reason I've decided to always color as green, is 30 degrees. All right, that means based on our work in the last problem that the cosine of 150 degrees will be more or less the same as the cosine of 30, right, which is root 3 over 2. But in this case it will be negative root 3 over 2. And the negative is very simple to explain. 150 degrees puts me in quadrant 2, where the x-coordinate is negative. It's that simple. Yet the sine of 150 degrees, well, that's going to be a positive 1/2, because in the second quadrant, the y-coordinate is a positive. Now let's take a look at 210 degrees. 210 degrees looks something like this. Right? That's 210 degrees. And yet again, it's got a reference angle of 30 degrees. So I can say now that the cosine of 210 should be the same as the cosine of 30, but again, it's going to be negative in this case because the x-coordinate is negative in quadrant 3. But so is the y-coordinate. The y-coordinate's also negative, so the sine of 210 will be negative 1/2. Again, it'll be the same as the sine of 30, but because it's in a quadrant where the y-coordinate's negative, it's negative as well. Let's take a look at the 330. 330 is larger than 270. It puts us all the way like here, right? That's 330 degrees, but its reference angle is 30 degrees. So the cosine of 330 degrees will be the same as the cosine of 30 degrees, but will it be positive or negative? Think about this for a minute. Now, if your instinct was, well, fourth quadrant's got to be negative, not true. In fact, in the fourth quadrant, the x-coordinate is a positive number. But the y-coordinate's a negative number, right? Down here, right? Y-coordinate's negative. And therefore, we get a sine of 330 of negative 1/2. So, reference angles are absolutely key in determining the sine and the cosine of angles that aren't between 0 and 90. Because if we know the sine and the cosine of the reference, we can find the cosine and the sine of the normal angle. All right, pause the video now and write down anything you need to. Okay, getting rid of this. All right, the last little piece, nothing to do with reference angles, everything to do with radians. All of the work we've been doing has been primarily focused on degrees. But every angle in degrees has an equivalent angle in radians. Equivalent, not coterminal, but the same angle, right? So we want to feel comfortable in evaluating sine and cosine using the unit circle diagram, but with angles that are in terms of radians. Now, eventually, you'll be able to just picture where all these angles are, and you'll know them automatically. But again, if I want to know what the sine of pi over 2 is, and I'm not sure what pi over 2 radians equals, although that's a very, very important one, then I would want to do the conversion, right? And I would cancel the radians, and I'd cancel the pi's, and I'd have 180 divided by 2, which is 90 degrees. So the sine of pi over 2 is the same as the sine of 90, and the sine of 90 is the y-coordinate at 90, so that's equal to 1. And you can verify that in your graphing calculator as long as you put it back in radian mode, right? Then you do sine of pi over 2 and you'll get 1. What I'd like you to do is try those last three. If you need to convert to degrees, go ahead and do it. And if you don't, awesome. All right, pause the video and take a little bit of time now. All right, let's go through them. Well, I'm not going to keep going through the conversions. You've done that on a few problem sets at this point. Pi divided by 3 is the same as 60 degrees. The sine of 60 degrees is square root of 3 divided by 2. 3 pi over 2, that's the same as 270 degrees. Again, a very important one. That's down here. The cosine is the x-coordinate, and that's 0. 3 pi over 4, that's 135 degrees. At 135 degrees, the x-coordinate is negative root 2 over 2. And that's it. So there really wasn't anything remarkable about exercise 8, but we want to keep using radians as much as we can so that we get more used to them. All right. Pause the video now and write down anything you need to. Okay, let's clear out the text and wrap up this lesson. So there really wasn't much that was new today. We wanted to continue to work with the idea that on the unit circle, an angle drawn in standard position has a sine that's given by the y-coordinate on the unit circle and a cosine that's given by the x-coordinate. Possibly the only thing that we did today that was different from what we did in the last lesson was this idea, this relationship between the sine and the cosine of an angle and the sine and the cosine of its reference angle, which again are basically the same numbers. It just could be different by a plus or a minus. All right. Well, thank you for joining me for another Common Core Algebra 2 lesson by eMath Instruction. My name is Kirk Weiler, and until next time, keep thinking and keep solving problems.